So for today we're talking about graphing trig, and I want to just go back to the unit circle. Remember the unit means 1, right? So all of these spots are like, for example, 1, 0, 0, 1. I'd like you to label all 4. -1, 0, and 0, -1. Now I'd like you to highlight the y values. Can you tell which function we're going to talk about first by me saying that? Sine, because sine is the y values, right? So do you get sine starts at 0? And then as we move around the circle, it gets to 1, and then we go back to 0 again. And then the sign is -1, and then the sign goes back to 0. And then it just starts that cycle over again, and it just keeps doing it over and over and over again. Goes from 0 to 1, back to 0, now to -1, back to 0. Okay, I think you get the idea. So let's see what it looks like. Would you agree? At 0, when we started, sine was 0. So it starts right there. So everybody put a dot right there. And then sine grows to 1 by the time you hit here. So by the time you hit pi over 2, that's this first stop. It was at 1. So sine goes up to 1. When we hit pi, it goes back to 0. And then when we get to -1, we're at 3 pi over 2. We're at -1. And then when we go back to 0 again, is at 2 pi. 2 pi and 0 match up, and there you go. That's what sine looks like. But does it just stop right there? No, you can keep going. So this wave could keep going. It could keep going forever like that. And it could also go into this, which would be into the negatives. This would be negative pi over 2, because we could go backwards on this circle, right? We could go backwards and we could get to -1, see? When we go back here, we get to -1. So there is the graph for sine. We could do the same kind of thing for cosine. But cosine is the x values, and so cosine would start at 1 and then go to 0. And then cosine would go to -1, and then cosine would go to 0, and then it would go back to 1 again. Let me show you what that would look like. Everybody, start at 1. Then go to 0, and go to -1, then go back to 0, go back to 1, and I like to say the cosine kind of looks like a valley. If you haven't already done this, do this. This is the parent graph of cosine. By the end, your graphs are going to be super complicated, and they always start with just cosine or sine. Or tangent, I guess. But we aren't even talking about tangent today. So, I want to talk about how to number these in the best way. That's 1 pi over 2. To get how I slightly changed how I would say it. Then this is 2 pi over 2. I definitely changed how I would say that. And then this is 3 pi over 2. And you see how it's got a nice little system? 1 pi over 2, 2 pi over 2, 3 pi over 2, and this is 4 pi over 2. Why is that system good? Because you're going to have to number these. And are you just going to memorize that this is 5 pi over 2? I hope not, because you can just use this system. What comes after 4 pi over 2? 5 pi over 2. See how it's really easy if you know what to count by? Now you might be like, but you always told us we had to reduce. In this one case, I think it makes more sense to not reduce. So I'm not going to take the angles on this unit and mark you down for not reducing them. So if you say 4 pi over 2 where you could have said 2 pi, I'll be totally fine with that, because I think this is the smart way to label your axis. Kids, how easy it is? 1, 2, 3, 4, 5 pi over 2 versus pi over 2, pi, 3 pi over 2, 2 pi. It doesn't like flow at all. Whereas if I say 1, 2, 3, 4, and 5 pi over 2, I could teach a kindergartner to say that. What's after 5 pi over 2? 6 pi over 2. They'd probably think it was about pies, like, you know, blueberry pies, but anyway. Okay. So that is the graph of cosine. How is it different than sine? Well, it's still a wave. In fact, I've told you before that sine is the boss function, because cosine is just a cheap copy of sine. It's just moved over a little bit. It's the exact same wave. It just peaks at a different spot and peaks there. Okay, so cosine is just a copy of sine. I'd like to think of it as sort of like a clone. But a clone is exactly the same. It is actually, if you can clone something, you got the same exact DNA, then it's exactly the same. But if there was a clone of you, would it actually be you? It depends on how you define you, but it wouldn't have the same experiences as you, and therefore, I don't think it'd be exactly you. All right, anyways, yes?
So would you recommend we do this same, like 2 pi or 2 cosine as well?
I absolutely do. Yep. And the reason is because when we change these, they can get really weird. Like if I multiply everything here by 1/2, I'm not going to do it all the way across, but that's something you're going to be doing in like 1 minute. Then all of a sudden it's 1 pi over 4, 2 pi over 4, and you don't have to like really work at it. It's just once you figure out, oh, it's 1 pi over 4, then it's 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, and it's super easy to count that way. Okay? All right, so why would you ever do that? All right, because sometimes you stretch it. Everybody, just for a second, consider what would happen if I times this by 2. Y equaled something, and now it's twice as big as it used to equal. Do you get the y just got twice as big when I put a 2 there? Y equaled something. A lot of people think, well, you should put the 2 here. That'll double the y. No, it won't. If you want y to double, you put it over there, because y equaled something, and I'm now timesing it by 2. So the y's double, so this all of a sudden becomes twice as tall. Now, could I actually make you redraw it? I could, but I don't. I just say you can change this 1 right here to a 2. Yes?
If you put the 2 next to the y, then
I get how you might think that, but nope. Let's say y equaled 6, and I want it to double. Would you agree I just doubled the y? 2 times 6 is 12.
You're not changing anything on the sine side. If you're just making y, 2, you write 2y equals sine x.
Oh, okay, wait. If I put a 2 here, that would not work, if that's what you're asking. And I was saying don't do that, because really, if you put a 2 there, to get rid of it, you're actually going to divide by it on both sides, and all of a sudden you thought you were doubling your y, but you're actually cutting it in half.
Yes, you agree.
Okay, excellent, we agree, and that's what I said in the first place. So I said, if you want to double your y, you got to put the 2 here, not by the y. Maybe you caught the not. Don't put the 2 here, put the 2 there if you want to double your y. Okay, all right, I think we just agreed. So this, if I want it to double, I'd have to change that also to a 2. So this is negative 2 and 2, and all of a sudden, you don't have to redraw the graph. You can just renumber the graph. All right. They're going to tell us a few things that are true about sine and cosine that are really important. I don't know why they're starting with cosine, but it's okay. We can talk about cosine. Its domain is from negative infinity to positive infinity. Do you get that? Just means you can do this forever in both directions. Like sine just keeps going, so is cosine. Keeps going forever in both directions. Its range, as in the highest and lowest it goes, is from negative 1 to 1. It is continuous, as in it doesn't have any gaps in it, just keeps going. And it's smooth, meaning it doesn't have any pointed edges. It's a very smooth graph. It doesn't go like, There are graphs that do that, but this does not. Okay, so this is smooth and continuous. And it's even. Ew. Do you remember even and odd graphs? How about even and odd powers? Does that ring a bell at least? Okay. Well, we have even. If it's an even function, this was an example of something that was even because it had y-axis symmetry. All right. Its period is 2 pi. That means it completes a whole cycle by the time you go from 0 to 2 pi. I like to count that up by going 1 pi over 2, 2 pi over 2, 3 pi over 2, and 4 pi over 2. But you know that 4 pi over 2 is the same as 2 pi, right? So the period of this thing is how long it takes to complete the complete cycle. That's called its period. Okay? And then you just do it over again. All right. So this is really confusing way that they wrote this, but the period of this thing is 2 pi over whatever's there. The amplitude is whatever's there. We're going to do this better on a different slide, so don't take notes on this one. This is called a phase shift, and that is basically your vertical up and down kind of move. I want to remind you, just look at this for a second. Do you remember in the good old easy days of graphing that if you did this, it was a parabola that was shifted in different ways? Remember the deal where this was, it seemed like it was left 3, but it was actually right 3 because you don't trust the inside? All those same rules work on sine now. So you don't trust the inside of the sine function. If you put a number in there, it doesn't do what you think it would. If you double the inside, it doesn't make it twice as wide. It makes it half as wide. Everything's the opposite of what you'd expect in there. Another thing was this was up and down, and another thing that was vertical, and it was horizontal stuff on the inside by the x, and it's vertical stuff on the outside here. Well, all those same things are true with sine. So get to this page, please, and this is where I want you to take the notes. You write this down, you remember it way better. And that's sometimes the difference between an A and a B. For most of you. Thankfully, most of the kids that were getting C's are by now they've probably given up and gone to regular pre-calc. But for most of you, the battle is between, am I going to try hard enough to get an A, or am I going to get a B? And sometimes I have a bad day and get a C. All right, well, this is the amplitude. You'll remember 10% of what I say, but a much higher percentage of what you write down. Activates a different part of your brain. This B is called the horizontal stretch / shrink. And I'm going to put something that you may not understand right now, but relabel x-axis. This is one of the key jobs you learn how to do is, when we were graphing this thing, and I was saying it goes to 2 pi, and this spot here is 1 pi over 2, 2 pi over 2, 3 pi over 2, and 4 pi over 2. If you put a number here, you would think you just multiply everything by that, but you don't. You divide everything by that. So if I put a 2 there, I'd put a 1/2 on everything. And that's the relabeling of the x-axis. We'll practice that again in a second, but notice that thing rings true that if there's a 2 here, you actually don't multiply everything by 2, you multiply everything by 1/2. Or another way to say that is you divide everything by 2. And then all of a sudden, this is 1 pi over 4, and yeah, I could reduce that to pi, but the way I'd rather, 2 pi over 4, I'd rather say 2 pi over 4, which can reduce to pi over 2. But 1 pi over 4, 2 pi over 4 is so easy. 3 pi over 4, and 4 pi over 4. Once you get used to counting it like that, then when I ask you, what's the next spot here? Because you have to shift it to the right. Then you label that spot and you say it's 5 pi over 4. Hopefully you'll get used to that counting up by ones thing. And why did all the numbers just change? Because if you put a 2 on the inside, you multiply everything by half instead of multiplying it by 2. All right, this C thing here, that is called a phase shift. This is new lingo, and you're going to have to know it. We can abbreviate it PS. Phase shift. That takes the whole thing and moves it to the right or left. It still does the same thing as you would think. It's on the inside, so that's right and left stuff. But that is called a phase shift. And last but not least is the D, which is the up or down. They call it something more fancy, but that's all you're really doing is moving it up or down. All right. Somebody out there not taking notes, I don't want to have a personal conversation with you, but please start taking good notes here and doing the problems with me. All right, so I'd like you to now graph this one. And to start with, by now, hopefully you have learned that sine starts at 0 and is just a wave like this. And you should be able to label these spots pretty easy, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. But change the numbers based on the fact that that's really a 3 and that's really a 4. So I would start with your original 1 and -1 and then go, oh, but there's a 3 here, so now I'm going to change this to 3 and -3. And I would start with 1 pi over 2, 2 pi over 2, 3 pi over 2, and 4 pi over 2, but then I would adjust it by this 4. And I just told you how to do it a second ago. Let's see if it's stuck. I'm going to pause and give this one a try. The amplitude is 3. It's right here. That's the amplitude. The amplitude is that first number. Okay, so the amplitude of this one is 3. Is that called the phase shift? No, it's right next door to the phase shift. This is called the horizontal stretch or shrink. Is that a stretch of 4? No, it's a shrink of 1/4. So, hopefully, you just went through and multiplied everything by 1/4. 1/4. 1/4. 1/4. Who had that done before I said it? Excellent. Now, could I have caught on that this was pi over 8 and just counted up from there? Yes, that's pretty advanced and faster and smarter. 1/8, 1 pi over 8, 2 pi over 8, I know it reduces, but 3 pi over 8, and 4 pi over 8. That's a great way to go. Because I know what you need to know when you get to the more advanced ones. We shift them to the right or left, and then you have to label it. And if you have some weird thing like just pi over 2 here, that doesn't tell you what comes next. But if you have 4 pi over 8, you know it's 5 pi over 8. Easy peasy. Okay, there. You've learned the basics of graphing trig. Now, you've seen sine, you've seen cosine. Sine starts at 0. Do you remember what cosine started at? 1 is correct. If you're ever not sure, if you go back to the unit circle, that spot right there tells you. At 0, what's the sign? 0. So at 0, you get 0. So 0, 0 is where you start sine graph. And this one's at 1. So at 0 degrees, you start at 1. So this is cosine starting at 1. All right. Cosine of theta, actually. All right. So this formula, I'm just going to give it a shout out, but we're not going to use it much today. But I'm telling you, on your test, guaranteed this formula is going to be a big deal. The period is 2 pi over b. Why is it such a big deal? Because if I know what b is, remember how I said we divide by it? So if b, that little number that goes right here, is 4, then you just divide everything by 4, see? But it also, if you have this little formula, period is 2 pi over b, I can tell you the period, which we do sometimes. I'll be like, here's a sine graph, but its period is 4 pi over 3. Well then, if you know this formula, period is 2 pi over b, you can just put, oh, if the period's 4 pi over 3, then I put that there, and you can solve for what b should be. All right, so moral of the story, know this little formula. It doesn't come up much today, but this is like one of those classic first days of the unit where I'm trying to show you almost everything in the whole unit. Your brain's probably full of things, but that key right there is going to come up big time when we get to the harder stuff. Period is 2 pi over b. All right, remember that the thing on the inside here is not called just right and left. It is called a phase shift. Those of you that are in, I think it's physics. Has anybody learned anything about phase shift in physics? I think it's a physics thing. Anyway, usually there's some kid who chimes in and says, yeah, we do that in science. All right. So let's say you had to graph this. What are the two changes from normal cosine? That and that. These are so easy. You just relabel your y-axis with a couple different numbers. This, I told you how to do it. We'll see if it's stuck. So cosine, would you agree, starts there, goes down into the valley, comes back up. And pro tip on making these, just graph the wave, then label it with 2 pi right there. And then go back to halfway. And then half of that. And go, well, half of 2 pi would be pi, and half of pi would be pi over 2. And then start counting up. 1 pi over 2, 2 pi over 2. 3 pi over 2 is the most neglected spot right there. People forget to label that. And 4 pi over 2. But you won't if you'd use this system, because you're not going to go 1, 2, 4. You're going to be like 1 pi, 2 pi, 3 pi, 4 pi. Okay, so 4 pi over 2. And this is 1, and this is negative 1. And hopefully that all comes easy. Now we just change it based on these two things. And relabel. You don't have to redraw your picture. Your wave stays the same. All right, compare this when you're done with the kid next to you. If you can do this and these, tell what A, B, C, and D are. By the way, if there isn't one, it's usually a 0 or a 1. There is always an A, B, C, or a D. It's just if they're you have to figure out whether or not things that are missing are 0s or 1s. Depends on the situation. All right. Pausing while you work this one out and then compare with the kid next to you. Okay, let's see how you did. Eleanor, what did you change based on the fact there was a 4/5 in the front?
I made the 1 4/5 and
Four?
the negative 1 negative 4/5.
You are exactly right. Okay, good. And a little harder question. Eleanor, you seem to be on a roll. This pi here, how would you change your graph based on that?
Okay, so I multiplied all of them by 1 over pi.
Ah, noticing a trend that it's kind of like dividing by pi, but I like to start counting by something. How did you start counting by then? Because those pi's would cancel.
Yeah, I just had 1 over 2.
Good, so then what's the next one?
2,
2 over 2, and what's the next one?
3 over 2,
3 over 2, and the last one?
4 over 2.
4 over 2. Don't do sideways fraction bars. Okay, and last spot, if you had to shift it over 1, would be
5 over 2.
5 over 2. And where'd the pi's go? Because we canceled them. They're gone. All right, cool. What was A? It's also known as the amplitude. Say it if you know it. 4/5. What is B? Pi. Now, some of you might be like, but I thought it was supposed to be outside. Couldn't I factor this out and put it on the outside? Sure I could. So therefore, it's pi. How about C? Well, there's nothing in here that's shifting it over, so then it's 0. And last but not least, what's D? What's out here? Can I put a 1 out there? No, then you'd shift it over 1, up 1. And so we don't want to have a 1 there, so we could put a 0 there just to hold the place, and that's a 0. And the horizontal shift is 0, vertical shift 0, period. Oh, period? Ooh. Well, period is 2 pi over b. Do you remember that little formula? What was our b? B was pi. Period is 2. How else could I have known that? Look right here. That's where it ends, right? It ends at 2. Period was 2. Yep. It's where the cycle stops and you're just going to start over again right there. So 2 pi over b. Just try to remember that formula. I said it would come up a lot later in the chapter, but I guess it even comes up now. So period is 2 pi over b, and the b was pi. So 2 pi over pi, so it's 2. And the horizontal shift was 0, amplitude 4/5. I think I've got those all filled out now. 0 here and 0 here. All right. You now know everything. Now let me just show you which ones I would do. There's way too many problems. Like if I actually assign that many, I think nobody would do the homework. I'm trying to keep it small enough so that you'll actually do it. And here we go. I would scribble out this middle one. Also, don't stress about the fact that there's all these little marks that are pre-made for you. I personally would just pick one of them and say, I'm going to call that 1, and I'm going to call this -1. And then I would draw my wave like that. And I wouldn't get super stressed about exactly how many marks did I go over. I would just say, that's 2 pi. That's pi. That's pi over 2. All I'm saying is you can kind of ignore the marks. I'm fine with that. I think it's way easier to not have the little marks. You could count and be exact about it. If you're a perfectionist, I get how that might drive you a little crazy. That spot there, most forgotten point. 3 pi over 2. It's got to be labeled. All right, there. And then this one, what's the one thing I need to change? The 3 has to go here and here. There we go. And can you label A, B, C, and D? The only thing that's hard is the period is 2 pi over B. Do we know B? Well, there's none, but that really means B is, what is right there? A 1. Can't put a 0 there, it'd cancel it out. It'd be like there's no angle. So you have to say B is 1 in this case. Well, that means it's just got a period of 2 pi. That makes sense. It's normal sine. It hasn't been stretched in that way. 2 pi over 1 is 2 pi. All right, so I think you should do that one, and I've done most of it. And then this one. On this page, I would recommend that you do also cross out the middle one. It's good for you to learn how to shift. These are where it gets hard. You're going to shift this whole thing to the right pi. And by the way, oh, wait a minute. This is a nasty one. Nope. Not ready for this one. So wait a second. Let me just show you something, but we won't do this problem. Why? Because that 2 needs to get factored out to the front. The 2, I don't know if you noticed that, but the 2 should be in the front. And if I do factor that 2 out to the front, I have to go divided by 2 here to make that work, process that. This 2 would be times by that, and it would times by that, and that would bring it back to pi. See what I mean? You'd have to factor that 2 out to actually do this problem, and that's a little too much for today. So don't bother with that one. But moral of the story, if you can factor it, you should. If I have sine of 3 pi minus 4, it's already factored. Yay, that one's good. But if you have one like this, sine of 3 pi minus 2, you have to factor the 3 out of that and make it like this. Sine of 3 parentheses pi minus 2/3. So that you can get this factored out to the front. It needs to be factored, otherwise things won't work. Okay, on this page, they're just all too hard. Skip them. Too much for the first day. We'll get to it. This, I would skip the last one, but I would strongly recommend doing these because it's a review of chapter 12, which is now 2 chapters ago, and I told you it's going to keep coming back. So some of the stuff that we do this chapter near the end is going to rely on you still knowing how to do this stuff. I'm going to put this over 1 to show you they just gave you 2 sides of a triangle. Did they tell you what quadrant to draw it in? Oh yeah, quadrant 1. So you're going to draw a triangle like this. They just gave you 2 of the sides. And it says sine is x. Ooh, that tells you something. Sine is x. Sine is opposite over hypotenuse. And then I think you'll figure out how that all fits in really nicely. Okay, so moral of the story. These will be a really good, powerful review that you should do if you really want to do well in this chapter. And this is the moment where you decide, am I going to get the B or am I going to get the A? Because if you take the time to battle through this and remember how this works and you look at the key for it, you'll be in good shape to get that A. All right, and this one, it's worthy. I would do this one. And the only thing that's scary is, how am I supposed to know where the square root of 2 is? You don't. You just label it, instead of 1 and -1, you label it square root of 2 and negative square root of 2. And you don't exactly know how big it is. I don't know, it's 1 point something, but you just label it as that. So don't stress by the fact that they use a weird number for that. But wait a minute. There's a cosine in the middle of this thing? That might be too much for some of you, but then I know you're going to go check the key and you'll figure out what they did. All right, so that's like your stretch problem. It's not impossible. All right. And that's all I have for you. Strongly recommend to do these, check them against the key. And now I'm going to hand back your tests from yesterday or whenever. Yeah, it was yesterday we took it.